course. In physics, we're looking at the topic static equilibrium. This is related to forces in two dimensions. So static, just what we're talking about when I say static equilibrium. Static is not moving. Equilibrium means happy. Okay, it doesn't want to change. And so what that means is you've got a system where the forces are balanced, therefore there's no desire to change, and you have no net force. Okay? When solving problems involving static equilibrium, it's not different than net force in 2D. It's just that net force is equal to 0. Okay, so in net force in 2D, sometimes you're solving for net force, sometimes you're solving for something else, but you didn't know the net force. Now, it's very specific with static equilibrium. If the question says to maintain static equilibrium, or it's not moving, whatever, net force is 0. And of course, static equilibrium is a critical thing to understand if you have an intention on being like a civil engineer, architect, because civil engineers and architects like to build structures that don't move. Unlike maybe a mechanical engineer, where sometimes you want things to move, but in structural engineering and such, you want things to not move. So here's our first example on static equilibrium. I'm going to do two videos, and the first video is just this basic one, no application whatsoever. We just have a free body diagram with 3 forces. We don't know the third. All we know is that this system is in static equilibrium, which means that the net force is 0. And the idea is this. There's different ways you can do it. You could actually, especially this one, it's only 3 forces, you could actually use sines and cosines, and I think that you will do questions like this in calculus where you do that, or vectors part of calculus. Personally, I think the concept of x and y components is more relevant, because essentially, if you have static equilibrium, not only do you have static equilibrium in the overall net force of 0 overall, the net force in the x direction is 0, and the net force in the y direction is 0. So when you're solving a question like this, what you do is you take the x direction and you solve for the net, well, you know the net force in the x direction is 0, but you can then find f3x so that is true. And similarly in the y direction, you can find f3y. And if you know f3x and f3y, at the very end, like we've done so many times, do Pythagorean theorem and you get your answer. Okay? So here's the solution. So we know this statement, the net force in the x direction is, sorry I'm jumping around, but I want to take a look here. So it's f1 in the x direction, which is up here, f2 in the x direction, plus f3 in the x direction. So we know that net force has to be 0, so this here is 0, that's why that's 0. f1x is negative 20 sine 20. Let's see why. I made a sign convention, and I could have been the other way, but I chose this to be positive. So this x component, if I was going to try to sketch it in here, this x component would be coming across like this, right, in this direction. So if that's the x component, then it's across from the angle, so it's sine, opposite, right? And it's negative because it's pointing, I decided that, this was positive, so this must be negative, okay? So that's why it's negative. Negative 20 sine 20. The first 20 is because of this, and then sine 20 because it's opposite. f2x is positive, because I said that direction was positive, it's the full 100. And then there's f3x, which is what we're looking for. So then I rearranged for f3x. All I did was I kept this here because it was positive, just move those to the other side, and f3x is negative 93, okay? Kept a couple extra decimal places. In the y direction, exactly the same idea. f1y is, this case, positive because of my sign convention, and 20 because this is 20, and then it's adjacent, it's touching the angle, so it's cos 20 degrees, plus f3y. I didn't, it's plus f2y is 0 as well, but since this is completely east, there is no y component of f2, and then the f3y is small, but it's there, right? So 0, right, same thing, net force is 0 in the y direction, so 0 will be 20 cos 20 plus f3y. Go ahead, find f3y with a sign, it's minus 18, which is about what it looks like, it's in the negative direction. Okay, it makes sense that both of those are negative. And now I find the overall. You draw, doesn't matter what you draw first, but the key, I want to say it again, the key is you start drawing, do the X first or the Y first. I just usually do X, but you don't have to. And you don't pick up your pencil. So you come across, don't pick up your pencil, come down, don't pick up your pencil. Notice I don't have negatives in here. I've told you this before as well. The negatives is sort of implied by the direction. So because I drew it in the negative direction, I don't need to give that a negative. Okay? And I'm going to solve for F3 using, this is just Pythagorean theorem, right? And find my angle using inverse tan. And that's my answer. And does it make sense? Well, if we look at it, you know, if this is 100, that looks like 95. I think it's almost the same size. And it looks like it's just a little bit south of west, right? And 11 degrees. So good answer. And that's just our first little example of static equilibrium in two directions. And we're going to do another example coming up.